So thank you very much for coming to the seminar. So today we have Dana Pousty, and then Dana is a multidisciplinary environmental scientist and also entrepreneur. And then she focuses on advancing equitable access to safe water. And currently she's doing a postdoc at CSU Boulder. And her research mainly integrates microbiology, photonics, and nature-based solutions for disinfection technologies. And in addition to research, like we mentioned, Dana is also the co-founder of Beyond Blue, an impact venture developing decentralized water treatment systems for low-income communities, and data pound and AI-driven water quality monitoring initiatives. For her entrepreneurship, she has been received many awards, including the top 25 female founders in water tech, the recipient of the IUVA Innovation Award, and the following awards, Female Science Talents Fellowships, and many other awards. So without further ado, let's welcome Dana for the seminar.
Thank you. Thank you so much for the introduction. Thank you for having me. So yeah, today I will mainly focus about my research when I started it during my master till today about photon-driven water disinfection. So we are talking about water. As we all know, 70% of our planet Earth is water, but most of these water are water with a lot of salts. There are the oceans, and then it's left like around 3% of fresh water. And from these 3% of fresh water, most of them are glaciers and ice, and we have not a lot of fresh water that we can use in order to use it for our needs. So this is the stress about the water, and this is why every drop is count. Typically, water contamination are divided for 3 different groups: chemical, physical, and biological pollution. I mainly will talk today about biological contamination, bacteria, viruses, protozoa, and biofilm. Which biological contamination in this presentation, I will divide it to 2 for planktonic cells, which we have some bacteria and viruses that just floating in the water and live there. And we have also biofilm. What is biofilm? Everywhere that we have surface, water, and bacteria, we will have biofilm. The bacteria is attached to the surface, and then I will say it in simple words, it will call to all their friends bacteria and will generate some robust structure of biofilm, which is a huge pain for water distribution system, water storage tanks, and it costs a lot of money to all the water utilities. So we need to find some ways to deal with that. And now this presentation, I will walk you through the electromagnetic spectrum and how it can affect and help us to solve those planktonic and biofilm stuff. So I will start at the UV spectrum, which I call it the magic light. Why it's the magic light? Because we cannot see it. There is the area of visible light, which we can see. There is the range of the UV and then the X-ray. But UV light we cannot see, and it's divided to 3 different ranges: the UVC, UVB, and UVA, which UVC is between 200 nanometer to 280 nanometer, then UVB from 280 to 315, and then from 300 to 15 for 400 for the UVA. Each range have its own characteristic, and we will talk about it more. So we have different kind of UV sources that can emit this kind of light. We have the mercury vapor lamp. I just want to ask if someone are familiar with UV technology, UV disinfection. Have you ever heard about that? No, okay. Parts say yes, parts say no. Okay, so we have like different lamps that can emit this kind of range. So the traditional very old technology called mercury vapor lamp, which is look like a fluorescent, but it's emit light on 254 nanometer. It's a monochromatic source. Then in the recent years, we have also UV LEDs. LEDs, as we all know, in our phone and television and everything, but they are just emitting the light in the UV range. And what is wonderful here that we can choose the peak. It can be on 250, on 254 nanometer, 270 nanometer, 300 nanometer, etc., etc. And we have also the cryptochloride excimer lamp, which is emit in the far UV 222 nanometer, which this kind of source is safe for human. Human can emit for this light. I don't know if you remember, but during the pandemic, there was a big buzz about those lamps that human can irradiate to this light, but all the other are not safe for humans. So don't try it. And if you ever like come across with those lights, keep safe. So what happens during like this UV radiation? So as you can see here, we have the UVC, UVB, and UVA range, and we have also the DNA absorbance. The DNA of every alive microorganism can absorb the light, and the peak is around it. Is in the UVC range, which is almost the peak of the mercury vapor lamp. So this is why it's very popular, those lamp. So what happens here? The DNA absorbs the light. The DNA is built from a small, tiny nucleic acid, which are builds the DNA, and they absorb this light, and then it's make the DNA since like it's like a double strand to detach to each other, and then attach to their neighbors, and then by that, like all the DNA structure just damage, and the bacteria, viruses, protozoa, and other cells cannot replicate, and it actually inactivate those bacteria and viruses. It's important to say that it's inactivate and not killing those bacteria because we are not killing them. In the UVB range, what happens, first of all, you can see here in this graph, the nucleic acid, the DNA absorbance, which it have like high peak at the UVC range 260 nanometer, and also the protein absorbed as well this UV light. Once the protein absorbed this light, so it actually also damaged the protein. In this UVB range, also some other camphor in those bacteria can absorb this light and generate some ROS. ROS are reactive oxygen species, which are a very reactive species that can oxidate everything in the cell, the DNA, the lipids, the proteins. So in the UVC range, we have a different damage mechanism, which is the indirect mechanism. So there is a various application for UV in water treatment use case. First of all, in the water distribution system, point of use, like in the faucets here, this like will be the point of use, point of entry, in storage tank, etc., etc. Now we will talk a bit about the LEDs, since it's a related. When I started my master, it was a new UV source. Now it's relatively a new UV source. So why LEDs? LEDs, first of all, it's a quick startup time. It can operate also by solar panel. It have long lifetime. You can choose the wavelength that you want to work with. And I will show you exactly why it is so important. It's not contain any mercury, so the disposal is relatively safe in compared to mercury lamps. And in the recent years, and of course, after the pandemic, the cost drops. Also, the well plug efficient is also increasing. So we were thinking, what will happen if we will take a wavelength from the UVC range and wavelength from the UVB range, combine between both of them? What we will see if we will combine the two different damage mechanisms, because now most of the water utilities, all the UV system are using only the UVC range. Just to remind, only the direct damage to the DNA. What will happen if we will combine both mechanism? So it can cause additive, or synergy effect. And what I mean in additive, if we will take the UVB, the UVC, we will sum the inactivation, we will get just the sum of the both of them, like 1 + 1 = 2. But the synergy, it tells us that 1 + 1 = 3 or even 4, and we can enhance the inactivation. So what is the log inactivation? Actually, now I will present all of my results with log inactivation, which is actually normalized for the initial concentration in a log scale, which means 1 log reduction is 90% of inactivation, 2 log reduction is 99.99%, 3 it's 99.9, etc., etc. So when we worked with a glass of water, a petri dish, and we put our microorganism here, we used Enterococcus fecalis and E. coli, which Enterococcus, it's kind of an indicator for sewage contamination. We find that when we irradiate 265 nanometer, which is the UVC, 285 nanometer, which is the UVB, we get a really high log reduction value, log inactivation, in compare for the theoretical sum. If we will just sum the 265 and 285, we achieve more than 2.5 log reduction, which is a lot. And we were in shock. And then we thought, okay, that's interesting. When we are combining both mechanisms, something happens here. And first of all, this mechanism and this like combination, it's patented combination. And at some point, it was also the basis for a startup that we try to initiate. But after that, we did it with a water that just stand there. We thought, what will happen with a flow-through reactor? Because in the real world, we need a flow-through reactor. So we talked with Aquasense, which is a well-known UV LED company, and we tell them, give us your reactor, and we want to change your board with the UV with the LEDs in there. They have only UVC, so we want to add to the UVC also UVB lights, and combine the DNA and the ROS and protein damage mechanism. So now I will show you the results, but I have to say that we tried around like 6 different reactors when we that we designed. So it was not like, yeah, let's combine this one and we will get what we want. There is an issue of a ratio between the UVC and UVB. As you see here, UVC, we have only 1 LED, and UVB, we have 3. And when we combined it and tried 1 liter per minute, we also saw a synergy above 1.5 log inactivation, which is also was a lot when we combining between both. And then we thought, okay, that's nice. But in the real world scenario, why did it help us? Like, it saves some cost, some money, some energy. So first of all, yes, as much as the LED, the wavelength is longer, the costs are reduced because we are like getting closer to the visible light. And also when we calculated the electrical energy per order, which is a kind of a concept, how much electrical energy required for this specific for each reactor. So we also found that the reactor with the combination of the LEDs are getting lower lower energy, need like lower energy. So that was wow for us. And now this project is continue to get higher like flow rates and try different other stuff with those stuff. So yeah, we found when we combining those both wavelengths, and when we combining 2 different damage mechanisms, we can achieve much higher log reduction value and save some energy and costs as well. So we have those LEDs, we have this wonderful technology. What are we doing with that? I have to say that during between my master and my PhD, I was going to travel in Ethiopia, and I was very young, and I went to some village there in South Ethiopia, and I asked them like, "What are you drinking?" And they show me some ponds, and then I felt like, okay, I'm working on a very interesting solution and technology in the lab. I cannot live my life that I will only produce some papers. I have to take it out and see what we can do. So we are collaborating with NGO. It's called Innovation Africa. They are working in all of Africa, and we work in a village that's called Namaseru in Uganda, in East Uganda. And then the first step was to understand the field and how we can adapt this technology to the field. So what Innovation Africa is doing, they are pumping the water. They are looking for some groundwater. They are pumping the water, stream the water to this water tower, store the water there, and then spread it to the community taps that spread all around the village. Hello. But the problem is that these groundwater, they don't supposed to be contaminated because they are groundwater, but they found some E. coli and total coliform in the water. So this was one challenge. The other challenge, it's in remote area. There is no electricity. We are depending only solar panel, and most of the people in this village are agriculture people, and the closest city is around 1 hour drive. So we found that the LEDs can be a great solution for that. Since they're scalable, they are low maintenance, they have long lifetime, they are very efficient for different kind of biological contamination, and it's chemical independent, which means that you don't like chlorine when you need to take the you need to store the chlorine, you need to know what are the dosing. Here, you don't need to do that. So we finally come up with AquaSense system, which we installed, and the installations took us around 2 years in order to understand exactly the field needs, because we have also some electrical budget, and we have pressure budget that we need to meet those expectations, and we cannot like use some reactors that have like a really need like a really high pressure in order to flow the water through them. And second, those systems are good for the Western world, but not for like intermittent electrical supply. So it was a quite challenge. And now I'm happy to say that those systems are working there, and they are disinfecting the water. In those 2 years that when we install those solutions, we find that the remote area, it's a quite of a headache, because you want to know what exactly happened with those systems in the field. So we build a kind of a remote, but we build remote monitoring system, which we can monitor every minute. We can get some data about the voltage, about the current, about the pump, how much the flow rate, about the filters that are in this area, and about each reactor. What is the temperature of the reactor? What is the performance of the reactor? And once we have some malfunction, we are getting some SMS to our phone. And once I was there, I trained 2 talented engineers that know how to work with those systems. They are getting a salary from us about this project, and they can just go there and take care of everything. So there is a lot of thing how we can continue and advance with all this, also AI and machine learning stuff with this kind of beautiful technology. We can predict the maintenance. We can just understand what is the pattern of when when those systems are falling, and then we can predict when we need to maintain those systems. We can optimize the reactors. Let's say, for example, we can install some sensors, learn how with those sensors, learn what is the water quality, and according to that, increase or decrease the intensity of this lamp, and by that, we can save some electricity. So post-implementation, I'm happy to show those results that these graphs are before the UV treatment, and the green graph, which is mean that there is nothing after the UV treatment. So we can see that there is a lot of total coliform in the water. The N here is around 77 sampling during more than a year. And E. coli is not present in the water all the time. This is because E. coli we find only during the rainy season. Because we are thinking that all the floods and the water just getting much more contamination. During this project, we also did a community survey in order to learn how people feel about the water, what they need to do in order to get the water to their houses, because the water, there is community taps, and it's not directly next to your house. So sometimes people need to go more than 50 meters to their house, need to carry more than one jerry can in order to fill the water and take it to the house. And it was very important to us to learn it because, and I will show you later about some project that we did in India about that as well. So now we will talk about the ABL, antibacterial blue light, which is in this range for 400 nanometer to 470 nanometer, which is a light that can also use for acne. Or some damage that people have some skin diseases. And usually I saw that people use it also in healthcare facilities in order to disinfect some tools. And I was thinking, let's take this ABL and try it with water. Let's see what happens. And now I will give you a little bit of background about that. I was a part of a delegation for South India, which we tested the water there in 3 different villages. And we did some also project when we taught a young woman there how to use sensor in order that they will get a salary and education. And what we found that people use a lot, like only storage tanks. This is how people live. And it was after that, that's why we also did the community survey in Uganda, because learn how to people use it. So people collect the water in specific these villages in India from reverse osmosis facility that spread in the village. And the reverse osmosis facilities give us like 0 E. coli, 0 total coliform, but once the water gets into the water storage tank, it's just contaminated with E. coli and total coliform. So what we can do with that? This is like a huge problem. Those jerry cans, storage tanks, whatever. So let's return back to the ABL. ABL, it's not a direct damage to the DNA. It's actually kind of a chromophore in the cellular, intracellular component absorb this light, and then it can get a lot of energy. This energy transform to the water molecular in those cells, and it creates some reactive oxygen species, which can oxidate all the intracellular component. So what we did, we want to understand what is the efficiency of this ABL for biofilm. So we grow some biofilm on a coupon. Coupon, it's a kind of material that we can grow on it, biofilm, and we expose it to light, the mercury vapor lamp, the 254 nanometer, which is the traditional light, UV LED 270 nanometer, and 405 nanometer as well. I use different kinds of materials which mimic the pipes and the inner UV LED reactors. And first of all, we did some surface properties characteristic. We want to understand what is the roughness of those surfaces. So we found that the PVC is the highest roughness. You can see here all the hills and valleys. And why roughness is so important? Because the biofilm can hide there and the UV cannot like get there. So we want to understand what happens there. We also try to learn what is the reflectance, contact angle, zeta potential, to know about the hydrophoby and the hydrophilic material, and about the electrical charge of the particles as well by the zeta potential. And here are the results. So x-axis is the UV fluence, is the energy that we are invest in order to inactivate the bacteria. And y-axis is the low reduction value. We have the LP, we have the mercury lamp, 270 nanometer and 405 nanometer. And we can see like two trends. First of all, we can see differences between the different lamp source, the light source, and we can see also differences between the materials. But the thing that it's very important to understand here, that with biofilm is very hard to achieve high log reduction, because it's, as I said, it's a robust structure of bacteria. And here with the mercury lamp and with the 270 nanometer, which we damage only the DNA, we didn't achieve very high log reduction value. But with 4 or 5 nanometer, we almost achieve 4 log reduction value, which is 99.99% of inactivation, which is a lot for this kind of area. Usually in papers, we will see like this range. So we were in shock and we were very happy to learn that, but there is a huge drawback that you need to understand: the exposure time. You can see the differences exposure times. In order to reach 2 log reduction here in 270, we need to irradiate 44 seconds, but with the 4 or 5 nanometer, it took a lot, much longer. To achieve 4 log reduction, we need to irradiate around an hour, which is a lot. And then we can think, so for what is good, like why we need it. And the idea here that with other lamp source, we are reaching a kind of plateau. We cannot achieve higher log reduction, even if we will invest more and more and more energy. We did also some biofilm morphology stuff in order to learn what are the differences in the morphology when we irradiate under 270 nanometer and 405 nanometer. We stain the DNA and we stain the polysaccharides. Polysaccharides is the glue of this biofilm. It's a kind of arms that the bacteria are generating in order to capture another bacteria and structure this. We find that at higher fluences, 405 present like lower morphology parameters in compared to 270 nanometer, which means that the 4 or 5 kind of degrade those biofilm structure. So for 4 or 5, there is some advantages and disadvantages. First of all, the cost is very, very, very low. For UVC system, we can achieve like thousands of dollars. This is like a couple of hundreds of dollars, which is nothing in the UV range, in the light disinfection technology. It's safer for human. It penetrates much better to the biofilm. This is why we think that we can achieve higher log reduction than the UVC, but it's required a very long exposure time. But there are some real life use cases for that, specifically in storage tanks, specifically in some spaces that the water just standing there and need every once in a while something that will irradiate. It can also maintain the UV after like UV irradiation. because UV, I didn't say it at the beginning, I said that it's wonderful, but UV, it has some drawbacks. That one of them, it do not have any residuals. So once you're doing a UV at the end of the stream, like at the end of the pipeline, the bacteria, there is no residual, and some bacteria can come back to life. So we need to think about some way to maintain this. So in these kinds of scenarios, when we can irradiate, I don't know, every hour for 2 minutes or something like that, the bacteria, it can maintain the UV stuff. So this is about some storage tanks, about UV and ABL range. And now let's talk in short about far UVC, and then a little bit about visible light as well, and what visible light can also do. So far UV is a narrow range between 200 nanometer and 230 nanometer. We have the excimer lamp, which is emit around 222 nanometer. Which is safe also for human. And why we are using that? In the last year, we find that 222 nanometer is very efficient for viruses disinfection. As you can see here, the peak of the protein and the nucleic acid is higher around 200 nanometer than the 260 nanometer. So this is the motivation for using this kind of a light. There are also some molecules that are absorb this light, and then it can generate some reaction. For example, nitrate, when it absorbs light, so you can see here the different reactions that happen, and it generates some other species, reactive oxygen species, nitrogen oxygen species, and it can maybe it can enhance the water disinfection, and we will see it later. So we compare between 222 nanometer and 254 nanometer, and I took water with MS2. With MS2 is a virus, and it's really very hard to disinfect this virus. It mimic cryptosporidium in the water. Cryptosporidium, it was very hard to disinfect, and chlorine was not able to disinfect the cryptosporidium as well. During, I think that the 80s, some very talented researcher, his name is Professor Jim Bolton, that unfortunately he passed away, but he was one of the founders of this UV technology. He found that UV can disinfect this cryptosporidium, and then everyone want to try this UV. So I took the water, add MS2, and add a different kind of level, different kind of concentration of nitrate. 0, which is blue, 4, which is green, and 8, which is the purple, which is mimic like real-world scenario we can find in the wastewater, 4 or 8 milligram per liter of nitrate. So when we irradiate with 254 nanometer, we cannot see any differences between there is no any differences. In order to achieve 2 log reduction, we need a lot of energy. But let's see what happened with the 222 nanometer. So 222 nanometer, when we adding this nitrate, we can achieve higher log reduction if we are not adding this nitrate. So it means that something happens there, and some reactive oxygen species, nitrogen reactive species are generated there, eating the bacteria, oxidate the viruses, and then it enhances the inactivation. So we wanted to understand exactly what happens there and which kind of radical are performed there, are generated there, sorry. So we have like the hydroxyl radical, and we have RNS, which is a reactive nitrogen species. So we use some quenchers that are reacting with those species. So the TBA react with the hydroxyl radical, and uric acid is react with hydroxyl radical and the nitrogen, and RNS as well. So yeah, here is the, and here the purple one is when we do not add any quenchers and nothing to the water. And the blue one is when we do not have any nitrate. So we consider that there are some differences in the inactivation between both of them, and we want to know why there is those differences. So when we are adding the TBA, which is quench only the hydroxyl radical, we are reduced to one log reduction, which means that all the hydroxyl radical, instead of reacting the MS2, they are reacting with the TBA. And then when we are adding the uric acid, it reacts with both, with the RNS and the hydroxyl radical. So when we subtract between both of them, we can achieve what actually happened with the RNS, and we find that the hydroxyl radical was dominated here. They are much more reactive than the RNS, so they are the dominated reactive species here. And I can tell you that regarding the MS2, it have like 180 proteins that coat the RNA of the MS2, and one protein which is very special protein. It's called the A protein, which is very sensitive to those hydroxyl radical and some other species. This is why we can achieve very high log reduction with the presence of these ones. And how it can be implemented in the real world, this is something that we are working on with a researcher, and we wrote some grant about that we have the aquaponics. Do you know what is aquaponics? In when we are like growing kind of a greens in a water that's stream and not like and do not need any soil, and they connected to this stream also some fish ponds in order to use the fish ponds nutrients for these greens that they want to grow. But there are a lot of viruses with those fishes, so, and a lot of nitrate as well. We can take advantage of this nitrate, install some system and see what will happen there. So this is something that also is ongoing right now, and I don't think that we have a lot of time, so I will talk like very quickly about visible light, which is the light that we can all see. And then like what leads me to the visible light is the aquaponics water are like outside most of the time, all those systems. So what happens with the solar when we irradiate solar irradiation on this kind of water? So I used MS2, which is the persist virus, and I use also Pseudomonas aeruginosa, which is a kind of a bacteria that we can find in those aquaponics. And under solar irradiation, we can see that we can achieve a kind of reduction. The aquaponics is the green one. So the aquaponics achieve higher log reduction than the PBS. PBS is a buffer, which is, there is nothing in this buffer, and the aquaponics, they are very turbid. So we achieve higher log reduction with that, and it was fascinating. And also with Pseudomonas, we achieve really high log reduction with the wastewater. Something it happens there, and we wanted to learn what, because I did not myself, but me and my students did this experiment so many times, because first I didn't believe like how solar can inactivate those MS2 and Pseudomonas, which is very hard to disinfect with UV, and there is no any direct damage since it's not UVC. There is no any protein damage since it's not UVB. It's not 222. So it was it is very fascinating for me, those results. Now we are using kind of a probes in this water that can tell us which kind of species, reactive species, are generated in this water. And this is like a result that I just need to digest, because I got them like last week. And we can see that we first of all, we tried to do the traditional, the hydroxyl radical, which is the orange one. It's kind of stable between all those waters. But singlet oxygen, we can see that for the aquaponics is very high, and with the wastewater, it's also high. The PBS results, I don't believe them. I don't know. But it's very high, the singlet oxygen. So something happens there. The next step is to understand also a little bit more about the photochemistry under solar irradiation and target another species to learn what happens there. And then also to do some gene expression for the Pseudomonas to understand which kind of damage the Pseudomonas is feeling. Is it the DNA damage that it's feeling? Is the protein or specific protein that we are targeting? Is the membrane is damaged as well? So this is the next step of this research. And what I wanted to try to show you here that photons are amazing. It's kind of like our source of light, and it also can help us to live in this planet Earth much better. Nothing can happen without all those people, without all, first of all this professor that opened their lab for me, all the doctor and the engineers and the students that I met along the way, and of course funding, which is very important. So yeah, thank you so much. And all we need is love and light in our life. So thank you for listening.
First off, we talk about the soft sensors, and you have the sensors from all those data, and also you use the soft sensor, the machine learning one. And then, but how much of the training sets you need to collect for the data so you can actually run machine learning models and then to use those?
Yeah, so all those soft sensors. So first of all, we found some open access data of India ministry that they have all this data for those soft sensors, and they have also data about E. coli and total coliform. And with that, we're trying to learn some patterns. If we have like X amount of turbidity and Y amount of dissolved oxygen, so we try to learn the pattern between of them, and then we train the machine. And after that, we collected our own data in India and train this one. The next step after that was, so first of all, I think that the main issue here is to find an open access data. Yeah, and governments, they have a lot.
Those data is like already for the point of use disinfection. They just like it's more monitoring data.
It's a monitoring data that they have to collect.
Yeah, but how do you find the like the pH, the UV absorption? They also monitoring the
They also monitoring the pH. They also monitoring.
transmission.
Yeah. They are monitoring everything. And also I think that like maybe in like I don't know what happened exactly in the United States, but in a lot of like in my home country, so they have to monitor all this data and publish it. And you can access that because it's free for citizens and everyone, so you can get this data easily. Yeah.
Thinking about water age, distribution system, and you have UV treatment in the beginning, during the bacteria, go back, I imagine. Is there any difference between the treatment with UV and the treatment with chlorination?
Yeah, so the treatment with chlorination, it have like first of all, there are some byproducts of chlorination that can harm to the humans, of course, first of all, but it also have residual. And this is why in United States and in Europe, people like in Europe, like they do not like how in United States they use chlorine so much. But in a lot of parts of the world, they are using chlorine because you have to have some residual in the water. So honestly, I do not believe in UV in point of entry because there is no residual, and you can just disinfect there and get some other bacteria in downstream. But it can reduce the load of the bacteria at the downstream, and it's worth. At the end, it's a question of how much money it save, and it can save some money. And also chlorine, the problem that I found that you need a specific dose and some skills personnel in order to operate it. So if you do not have that and someone did a mistake, it's harmful. And there is a lot of years ago in Canada, in some city there, the name is Walkatron. A lot of people died because some drunk person, when he was like in charge of the chlorine, did his shift. And so yeah, I think that maybe the combination of both of them and will be great, but it's also depends on the application at the end of the time, like what your target is. Because for point of use here in our faucets, UV can be amazing. Yeah.
Maybe experiment or test to check. I know some of them in the villages, they put their water in glasses, like, so that they can have, like, expose them to sunlight, which is some form of disinfection. Did you try to compare to see if that was more effective than how you presented to them?
No, because we didn't see people that did that. In our survey, we first of all asked how people store their water and how people treat them. And in our specific village that we worked in, people didn't do that. So we didn't compare, but people use sometimes like mash or some herbs in order to disinfect the water. And some people in those villages, some people have like a lot of like understanding about the water. So they also have like a secondary tank, which is like a very clean tank, and some do not have. Yeah, but I hope that someday I will be able to compare between both of them. But I know that like the solar disinfection and how people use it are very effective. So yeah, there is tons of research about that. Yeah. Yes.
Do you think in the US, like you're implementing in India and Uganda, but like with the AquaSense stuff, do you see it having applications in the US? Would you feel like the treatment process it doesn't match up with what you're doing? Or?
There are applications of AquaSense. They are now they have so first of all, for point of use, they have like a lot of people. I don't know if people, but there are a lot of like, this is a very successful company that mostly worked in the United States and Europe, and not like in low remote areas. So they have a lot of like systems for taps and point of entry as well for buildings. Now they are also trying to get into the wastewater area. There is a project that we are working with Halifax in Canada, with Chicago, Boulder as well, and Vegas, when we are implementing some really huge reactors in these wastewater facilities, and we see a great result. And we are comparing it to the mercury vapor lamps as well. So yeah,